Hello, my name is Sean Singleton and I will be speaking about the use of infrared spectroscopy for drug analysis. Due to infrared spectroscopy's abilities to determine functional groups in organic molecules, the application of this method to the analysis of drugs goes without saying. It is used in creating potential new drugs, in the quality control department of pharmaceutical manufacturing plants, and in the identification of seized illicit drugs. Infrared spectroscopy, specifically FTIR, is ideal for identifying unknown substances. The technique is fast, easy and versatile and can analyze solids, liquids, pastes and gases. The frequency found from a spectra is proportional to bond strength. The force constant can be defined as the force needed to vibrate a bond by distance x is proportional to that distance. The force constant can be determined with the following equation, where f equals frequency, c is the speed of light, k is the force constant, and 1 and 2 are the masses of atoms 1 and 2 in grams, and an is Avogadro's number. Due to the nature of molecules, each has a unique combination of bonds. IR spectroscopy allows us to identify the bonds present, and thus we can identify the sample. IR spectra are the method of communicating the bonds present from which we can determine the substance. The table shown here tells us what frequency we should expect to find each bond at for each functional group. The table also tells us the force constant for each bond. This table is extremely valuable when trying to identify each functional group from a spectra. Here we have an example of a spectrum which is divided into sections of where each type of bond is expected. On the left we have the strongest bonds, the larger molecules bonded to hydrogen, e.g. oxygen and hydrogen, nitrogen and hydrogen, and carbon and hydrogen. The next section is where we find triple bonds, for example, carbon triple bond carbon and carbon triple bond nitrogen. The next strongest bonds are double bonds, for example, carbon double bond oxygen, carbon double bond nitrogen and carbon double bonded to carbon. The weakest bonds are on the right. These include carbon-carbon, carbon-oxygen and carbon-nitrogen, along with various other elements which will bond to carbon. Here we have an example of a spectrum. There are few peaks which suggest it is a small molecule. We have a peak with a wave number of higher than 3,500. We have a large double peak finishing at 3,000, as well as peaks between 900 and 1,500. After careful consultation with our chart, we can conclude that the peak that is past 3,500 is an OH bond, the double peak under 3,000 are CH bonds, and the peak at 1,050 is C and O bonded. We can come to the conclusion that the substance is ethanol. This chart is slightly more complex, indicating a molecule with more varied bonds. The wide group of peaks between 2,600 and 3,100 is indicative of a carboxylic acid. After consultation with our table, the peak at 3,100 is a CH bond, the peak at 1,690 is a C double bond O, the peaks at 1,600 is a C double bond C, the peaks between 10,050 and 1,300 are a CO bond, and the peaks at 690 and 900 are CH bonds. With these deductions we can conclude that the molecule has an aromatic ring and an acidic component, so it is likely the substance is benzoic acid.